So without further ado, I present to the club Doug Robbins.
Hi, everyone. Thank you so much for having me, and thank you so much for your generous grant. I'm really excited to share what I've been working on with you guys. So I'm going to share my screen right now. Can everyone see that?
Yeah.
Yes.
Awesome. All right. So as Cindy said, I am exploring the Talapis-Katsuk scoria cone complex in the Cascades. So this is me in the field and a little bit about how I got involved in this project. I discovered my love for geology a little bit late compared to most college students. I am in my other life, I study international economics as my primary major. And so as a result of the pandemic, most of my geology experience has been online. And so coming into my senior year and in-person classes, I really wanted to get more experience with hands-on science. So I knew I wanted to do a thesis. And most of my family is from Hawaii, as also mentioned. And so I really wanted to do a volcanology thesis. And the Cascades just made the most sense. Dr. Tollo has just an incredible amount of knowledge about this region. And so it really just made the most sense. This deposit in particular is really fascinating. It is a really interesting interaction between glaciers and mafic volcanism. And originally this project, we thought we would be investigating pelagonites. And pelagonites are essentially a product of volcanic glass alteration, specifically caused by contact with water. And while there are some present in this deposit, there are a lot less than we previously thought there would be. And so this project is pretty dynamic right now. Even now, we're still deciding what the final product will be, what this investigation will look like. But for now, I'm going to present to you guys the interactions between the glacier and the mafic volcanism and the implications of this for the greater Cascades region. So this is a map here of the Cascades. As you can see, this range of volcanism is massive. It spans from Northern California all the way up into Northern Canada. And as you can see in Oregon, in Southern Oregon, not only is the Pacific plate subducting under the Western US, but also the Cascadia region is beginning to rotate. And so it makes for a really, really interesting volcanic setting. This was my study area, so we were based out of Bend and just north of Crater Lake National Park, which is in Mount Mazama. And the Talapis-Katsuk is right under South Sister, if that orients you. So this map is from Scott and Gardner in 1990. It is the most up-to-date geologic map of this region, the South Sister, Mount Bachelor area. And it's very interesting. Scott and Gardner were a glaciologist and a paleomagnetics specialist. So two very interesting combinations that created this map. Zooming in a little bit, you can see the Talapis-Katsuk is this oblong kind of orange shape. And it's a very, very complex area, as I've said before. Here's some different, an assortment of the surrounding geologic settings. So you have basaltic andesites, silicic deposits, and other basaltic flows. The Talapis-Katsuk is pretty highly basaltic. So then this, even farther, I was on the northern end of the Talapis-Katsuk Butte. So right here, Devil's Lake is that little white area. And then I was just north of that. So here's a great view from the street. It really highlights the different volcanologic products of this area. So on the left here, or on the right here, is a really large rhyolitic flow from South Sister. And just down the road is this heavily mafic deposit from Talapis-Katsuk, which is off out of view to the left. You can see the van is for scale. It's a really nice indication of the geologic landscape. So here's an up-close look. It doesn't really look like much, I think, to a non-geologist, but I'm very excited about it. So it's really interesting. You can see there's pretty defined layers. Each one of these, pulse 1 and pulse 2, were deposited as lapilli expulsions from the Tolapis-Katsuk that then fell down the plateau and were deposited here. They're interlayered with some pretty well welded ash. And then this orange layer on top is an oxidation zone. It might be cross-bedded due to the angle, since it is going down from the plateau. And thus it also may include a transition zone from where these layers are mixing. And then the bottom is just the wash from weathering as it is exposed. Here I just wanted to highlight the different textures that were pretty visible to us while we were in the field. So there were quite a bit of inclusions, which had a wide range of compositions, as well as some lapillistones, which were pretty large and definitely had a large region size. So moving on to the thin sections and what I've been seeing so far, the lapilli have been highly vesicular and extremely glassy. The small microphenocrysts that you see here are vaguely similar in size and are pretty tightly welded together. The high vesicular nature comes from the lava being erupted into a steam, likely steam, could be water as well, but then being frozen as this kind of like foamy material, and then being deposited into this deposit. Here again are some more beautiful textures. This is pretty incredible to look at, but it shows a wide range of textures as well. You can see vesicles up here on the top right corner. The welded basaltic glass is this darker region. That's because it's a more mafic basaltic glass. And then as well, there's some plagioclase microphenocrysts. So I want to switch gears here a little bit and talk about the formation. So Scott and Gardner have proposed that this Tolapis-Katsuk butte was formed under a glacier. And so essentially, you can see in this diagram here, but essentially as it erupted, it melted the ice on top of it and kind of pushed it aside. And as this ice was moving down this map, so from South Sister, which is this gray area on top, down, it kind of made way for itself. And that's why it has this really odd kind of characteristic oval shape. This is pretty rare. There's not a lot of regions that have both mafic volcanism and glaciers, although Iceland is one, which I'm sure we'll hear about later. But I want to talk about, Scott and Gardner have never proposed any proof for this mechanism. This was just something that they thought could have been and proposed it. And most of pretty much everything that we've seen in my thesis so far has proved that this is the case. So here's some inclusions that we found. As you can see, there's a really, really wide range of compositions and textures. But I want to talk specifically about the darker one and closer to the palm of my hand. This is it in the thin section. You can see it's highly vesicular. It has small phenocrysts, and the abundance of vesicles both indicate quenching. So this was that foam that I kind of mentioned earlier. If you imagine like a bubbling pot, this was essentially a bit of froth or foam that then quickly cooled, broke, and then was deposited here. It can't be a normal lava because it's composed entirely of glass and with only very small microphenocrysts. And then the similar size bubbles also indicate that that wouldn't be the case. So here is a nice pyroxene crystal as well as a vesicle. Here is a really nice basaltic inclusion. It's very fine grained, and again, a similar size microphenocryst inside show that it would be a quenched, and it's surrounded by this really nice mafic glass. This is a lapillistone within the deposit. Again, extremely vesiculated. This would be one of those froth inclusions. And then on the right here again is the glassy matrix. Finally, this is a pelagonite. So this was kind of the basis of what Smith and Gardner had proposed for this deposit. And there aren't quite as many as we had expected, which is why my project has changed as time has gone on. But we do have evidence of some being there. And all of these kind of show that this deposit had strong water or steam interactions, likely steam because there's not as much pelagonite as, again, we had expected, but it is present. So going back into this deposit, I was on the north of the Tallapooskatsak Plateau. And this deposit is really unique because it isn't on the plateau itself. It's essentially where the ice would have been. We know that it was deposited after the Tallapooskatsak Plateau had mostly been formed because of the angle in which it was deposited. But that's pretty rare for it to be deposited directly onto the ice. And we know that the ice was still around as it was deposited because there would have to have been a water source for the pelagonite and the froth to be created. And so for it to be on the north where the ice was coming from, there would have had to be some sort of crack or crotch located in the ice for it to be deposited and then not washed away as the ice continued to move. And this seems pretty implausible, but there are real world examples of this. So here is the Cephalabrine Glacier located in Vestland, Norway. And this is just one example I found on Google Earth of something like this happening. So zooming in here on the glacier, you can see that the ice is moving down the screen, but in this little rock, you can see the ice move around this northern area of this rock outcrop. And this is likely where my deposit on the Tallapooskatsak Plateau would have been deposited. Again, this is a little different because it's not active volcanism, so there's not as much of that melting process going on. But Piedmont glaciers do move in this way. And so here's another example of the nearby Flatbrian Glacier. So just another example of how this could have formed and not been washed away. So we know now that the Tallapooskatsak Plateau was formed under a glacial setting, and the deposits that we found so far do support this. And if you look at the shape, that also is very indicative of glacial setting, as well as these, which are both glacial or alluvial deposits. So we know that, we know that the glacial deposits must have been, again, related to its formation. And then farther south outside of this picture are even more glacial wash deposits. So this is a photo of Mount Mazama erupting. And I want to talk a little bit about the geologic significance of what this all means. So the Cascades region has both glaciers and volcanism, which is, again, is pretty uncommon. Here is Mount Mazama erupting with glaciers on top of it. It's a really beautiful painting. But the two interacted on Tallapooskatsak, which again is pretty uncommon, and it created a wide range of inclusions and really unique deposits. The deposits themselves that we were looking at are, again, really unique in that mostly they would have been washed away. It's pretty rare for deposits not on top of a plateau to not be affected or completely moved away by glaciers themselves. And so it was extremely fortunate that we were able to find what we did find. And it again just shows the uniqueness of the entire situation. As I mentioned before, my project is still ongoing. I have a lot more to uncover, but it's already incredibly exciting. I'm very pleased to see where it's going to go. And then I should be writing a little bit about it in one of the upcoming newsletters, so you can see more progress that I've made. But that's all I have. I hope you guys have enjoyed this presentation. Does anybody have any questions about anything I've said so far?
That's pretty cool. It's definitely a unique setting. You know, it does remind me very strongly of Iceland and the volcano about 12 years ago, 10 years ago that erupted underneath the glacier, causing worldwide havoc.
Yeah, absolutely. Yeah, I mean, between the volcanism and glaciers at the same time, as well as that little area in the ice for this to have been deposited and not washed away, it really is incredibly unique. So it's been a privilege to explore it.
It looks like there was strong lineation between the sisters, I guess, and down through Sparks Lake. Is there a fracture of some sort or a fault? What's happening there? Like if you look at the geologic map.
Yeah, I can pull it up. So South Sister is pretty heavily rhyolitic. Let's see if I can go back. Wait.
Oh, I like that one.
So you're saying right here with South Sister?
Okay, where's South Sister? Can you put your arrow on it?
Yes, so South Sister would be here.
Okay,
so all
yeah,
of these are
that, and then down through
places.
Sparks Lake or whatever the name of the lake is below it. It just seems that there's a strong north-south lineation.
Yes, I think that has to do with the compositions of the surrounding volcanoes. I don't know super well the timings of each, but South Sister is rhyolitic, and this area, the pink area, is Egan Cone, and that's basalt and basaltic andesite. And so there is compositional differences between the magma supplying each, and so they have different sources. Dr. Tollo might be able to answer more of the timing in terms of the glacier and then also the active volcanism.
Sure, if you can hear me, I guess. That's a very good observation about the north-south alignments. It's very common in the central and northern Oregon Cascades to have these alignments. You can even see on here, way over on the right, there's a series of rhyolite lava domes, and those are also oriented north-south. Nearly everything is oriented north-south, and you hit it right on the nose. There are fissures here. There is a lot of faulting, and those fissures acted as vents for all kinds of volcanism, from mafic to silicic, from Pleistocene to pretty recent. The fissures are common in this part of the world because of two reasons. They're associated with back arc spreading from the Cascadia rock to the west. That's number one. And number two, they are related. You're in the northernmost basin and range here, the very, very northernmost. Just the place where the basin and range stuff becomes just about unrecognizable. But those are also north-south faults. That, coupled with the clockwise rotation of Oregon, enhances those faults, which become the fissures, which make the vents, which produce the linear volcanic terrains. Yeah, good observation. Very good.
Thank you.
I was wondering if there's much scoria developed along there with the interaction with the steam, or no?
Yeah, there definitely is. A lot of the scoria is actually on top of the plateau itself. So over here, most of what we found off the plateau has been lapillistones, but there is quite a bit.
Okay.
Some great questions. Anybody else have a question?
Doug, what's the age of these deposits?
Dr. Tollo might be able to help me with this one, but they're fairly recent. I believe Holocene in age.
Yes, that's absolutely. They are. They've never been dated directly. They're mafic, and it's very, very hard to do that. And there's been no charcoal found in association with the Talapas and Katsuk volcanoes, nor the plateau. So the ages have to come from stratigraphic constraints, mostly between the igneous rocks of the Tallapoosa Plateau and the glacial deposits that Doug mentioned, which really surround the area. And there are different advances and retreats. So if you're very careful and you look at the stratigraphic relationships, and this is where scoria comes in, because scoria it is in fact interbedded with some of the glacial deposits. Then if you do all this and put it together, the age of the Tallapoosa rocks are about, the age of eruption would be between 7,000 and 18,000 years. Quite recent.
Yeah.
Wouldn't there have been extreme explosivity or whatever with water hitting? Presumably could also trickle down, if it was glacier, into the magma chamber.
Yes. So these deposits are heavily pyroclastic. Most of what a previous student saw on top of the plateau, since I didn't go up on top, but another student did, was almost all scoria. And then these also would have been thrown from the volcano onto the ground to have been deposited. Probably what had happened is Scott and Gardner proposed that the water source was glaciers that were on top of the volcano that then melted and dripped down into the magma. And then as those interacted, both the water and the steam caused some pretty violent eruptions.
But I was thinking they could be blown, I don't know, many hundreds of miles from what we've seen in other places, even in the Basin Range.
It's possible. This age and also the presence of glaciers makes it unlikely that it would have come from another region, especially as all the surrounding volcanically active areas don't match up in terms of the chemistry. They're mostly basaltic andesite, whereas this is pretty heavily basaltic.
I guess I was just thinking that if there was that much glacial participation as a water source, it would have caused an explosion or explosions, explosive events that would have distributed the pyroclastics very far, and that could also be used as a means of proof that there might have been glaciation to provide the water and the explosive interaction. But if there isn't anything way far away, then the explosion was more contained, or the whatever caused the pyroclastics would have been more contained.
I see, yes. I'm sure there is. Like I said, kind of south of the Tallapoosa region, there's a lot of glacial deposits that are all glacial wash that everything the glaciers have pushed down. And I'm sure that there's bits and pieces of Tallapoosa scoria mixed in along with everything else there. I don't know how much work has been done on that. This region, and specifically the Tallapoosa, hasn't been extensively studied before. But I would definitely be curious to see how much of that glacial wash is from the Tallapoosa.
Thank you.
Thank
Very
you.
interesting.
Thank you, Doug.
Of course, thank you guys so much. It was a pleasure presenting to you.